Welcome, everybody. Great to have you here. A beautiful, sunny, and cold day in New York City. And for me, it's coming back home. I grew up here, and so it's always fun to come home. Before I even get started on anything, you saw it before you, if you noticed, the contributors flashing up here on the screen. It takes about 3 minutes to flash through all of them. I just wanted to sort of call out as clearly as I can how much we value those community of contributors and those people who have added both code, thought, PRs, a variety of different stuff to the whole Influx platform. And I just love to give those folks a hand just right here today. So we sort of have a saying around the office at Influx: nothing good happens until somebody downloads a version of the open source software. So in our way of thinking, nothing good happens unless it starts with the community for the company. And that's a really, really important concept for us. And so when we think about Influx Days, we don't think about it as a commercial for Influx at all. We think about it as broadly the beginning of a large community that we expect to form over time, not just around Influx specifically, but around time series, around instrumentation, around control and monitoring systems generally, both in software and in IoT. And so we try to create a balance in the agenda between some stuff on Influx, because we know folks are interested in Influx and the platform and where it's going, and then some stuff on even competitors' stuff in time series and that sort of stuff, and some stuff in customer applications, and some stuff just in the theory of time series. And this is the second time we've done Influx Days. The first time was in San Francisco a few months ago, and that went really well, and it was pretty exciting. And so now we're sort of committed to this model. So we have London coming in June. In addition to that, on a regular basis, we're going to have time series meetups in New York and in Denver and San Francisco, and eventually in Europe also, so that we'll have regular time series meetups in which we'll cover topics, again, not just Influx, but clearly on time series and instrumentation. Tomorrow here, I think you guys know that there are workshops. There's not a high hurdle to sign up. If you haven't signed up already, just let us know so we can get you a lunch or that sort of stuff. But the workshops will be happening tomorrow. Before we get started, I wanted to talk a little bit about the funding announcement that was handled this morning. I don't know if you guys noticed, but this morning we announced that we raised $35 million from Sapphire Ventures. And I think that's relevant here in the community, not because it's a big deal to raise money. It's more important to make money long term than it is to raise it. But it's a big deal because what it says about a couple of things. One, about the marketplace that we're trying to serve, this notion that we're broadly instrumenting large portions of our infrastructure. In the physical world, that manifests as IoT, as more and more sensorification of the physical world is happening. And those of you who are working in the software world, and obviously with the ephemeral infrastructure of containers and microservices and VLANs and the variety of different services that need to be instrumented on the software world, that is also, those instrumentation workloads are going through the roof. And so the funding is a validation of that. But I think the good news for us is that we are deeply committed to the open source platform. And so as we look forward over the next year, our intent is, and if you're interested, you can look at Paul's blog or my blogs went out this morning, is to nearly double our development staff, which is already fairly large for the size of company we are. And we're very committed to building out the next generation of Influx, which Paul will talk about in a little bit. Before we get started on that, I wanted to thank, first of all, the organizers for help getting us together. This is what a great venue. To be able to look out at the Brooklyn Bridge while you're eating lunch and that sort of stuff is pretty special. And thank all the folks who prepared speeches today, presentations. I want to thank the folks from Tesla, our customer, who's coming to talk about the work that they're doing about Powerwalls, and Comcast, who's also going to present today. I want to thank some of the other presenters, Tom Wilkie coming, and the guys from Sensu. And so I think it'll be a really rich day. With that, let me make the introduction let me make the introduction to Paul Dix, our founder and CTO, and my partner in this crazy enterprise. As many of you probably know, Paul had a vision 4 years ago of the idea of a purpose-built time series platform. And at the time, most of the platforms were being built on Cassandra or HBase or historically even on Oracle or MySQL or older platforms. I think Paul's vision of trying to build something that was purpose-built that developers could get installed relatively quickly, as Paul calls time to awesome, is a super guiding light for us as a business, right? Our view is, again, nothing happens till somebody downloads the open source. That's all about the community, and that's about developer productivity. Good things happen when developers can be productive. And so as you think about Paul, one of the things, and this is, I'll embarrass him a little bit, is I think of Paul as a developer's developer, somebody who cares deeply about what that experience is like and what it's like for people to do that. And that vision has been truly a guiding light for us. And so what Paul will be talking about today is the IFQL, which is the next generation of the query language and the future of InfluxData. And I'd like you to hold us and Paul and me accountable to that whole idea of developer productivity as a guiding light. With that, I'm proud to introduce, I wouldn't say this to him in person because it's embarrassing to compliment him in person, but I'm proud to introduce our founder and CTO, Paul Dix.
All right. Thanks, Evan. Hello, everybody. Thank you for coming to the Financial District and joining us here in New York. So as Evan mentioned, I'm talking today about IFQL, which is our new query language, and broadly about the future of the platform that we're building. But before I get into IFQL, I actually wanted to talk about how, like the journey for how we've arrived to where we are now and why we're doing the things we're doing in the language. So it's kind of like an evolution of a query language over time, and really an evolution of a way for working with time series data. So in 2012, I started the company as this company, Airplane, which was a SaaS product for doing real-time metrics and monitoring. And I used web services. I created a time series database, which is basically web services written in Scala, using Cassandra as the underlying store and Redis as basically a caching and indexing layer. And I exposed this via like a REST API, through a REST API, which was obviously popular at the time. And then 6 months later, I decided to rewrite this thing in Go using LevelDB as the underlying storage engine. So then it actually started to resemble an actual database itself, but still it had this REST API. So that product was not very successful, but what I saw was that a bunch of people were solving the same problem, right? They're trying to solve the problem of how to store and query their time series data. So we decided to take the infrastructure that we had built, start it as a new project, and create it as an open source project. And at the same time while we were doing this reboot, we decided, well, let's get away from the REST API and let's add a query language to it. Because I had this epiphany, like I was talking to a user and I was trying to explain the API to him, and he said, oh, well, I guess that's just like a group by in SQL. And I was like, well, yeah, maybe it is. So SQL is a language that people understand, so if we layer that on top, that'll be an easier way for people to work with this data. And it looks vaguely familiar, right? This is a query where we're looking at the 90th percentile in 10-minute windows of time for the last day for a specific host. So fast forward about a year, and the version of Influx that was out at the time was 0.8. And I was like rethinking the entire thing. I was trying to take what we had learned over the last year and think about how we could make the product better. So this was the 0.8 to 0.9 shift. So for any of you who have been using or following us for a very long time, you know that there was a breaking API change that was rather drastic in that chain, in that version transition. And the truth is 0.9, for all intents and purposes, was a completely new product. Like 0.8 of InfluxDB and 0.9 of InfluxDB could have been named something else completely because they're very, very different. But the big change at the time was we added support for tags. And I gave a series of talks in the fall of 2014 to try and figure out what was the easier way for people to work with metrics data? And to me, the thinking at the time was either you have tags, which is what we have now, or you have hierarchies like you see in graphite. And ultimately, we decided on tags being the better approach, and I think over time that's been proven out as Prometheus uses that model as well. But at the same time, in 2014, I was also thinking about the query language. And I was thinking at this time, well, should we have a query language that looks like SQL, or should we have something that looks like functional? So when I was giving these talks in 2014, I asked the audience, and I'll ask everybody now, who thinks SQL is a better way to query and work with time series data? That's one. Okay. Who thinks a functional style is a better way? Okay. That's less evenly split than it was in 2014. My bet was actually going to be there was going to be a 50-50 split, which is what I saw in 2014, because it seemed that people they liked the SQL language. It was like a comfort blanket, right, that they could wrap themselves in. So ultimately, like my belief at the time, and still now, is that a functional style language is actually a superior way for working with time series data. And I'll show some examples in a bit. But in 2014, I was afraid to make the switch. I already knew I was going to be making a breaking API change with the tag stuff. I didn't want to change everything all at once, and I was afraid it would just kill the entire project. So for better or worse, we've dealt with the language as basically like the language then is very similar to what it is now. And over the last 3 years, we've seen problems that have arisen from that. Feature requests that people have that we'd like to address that we haven't been able to. And some of those things are related to the query engine itself, but some of them are also related to the language and our ability to add to it without creating this weird thing where the semantics of it don't quite make sense anymore and it's hard to reason about. Ultimately, the whole thing is proven difficult to improve and to change and iterate on. And the truth is, it's not SQL. If you throw it at a SQL parser, it will barf on you because it's like a mutant strain of SQL. It's not the same thing. And for people who actually really know SQL, I've seen them be frustrated when they try to adopt the language and write some queries, and it doesn't behave exactly as they'd expect because there are some differences. So in 2014, towards the end of 2014, I raised the Series A with the pitch that we would build these other parts of the platform. So in the fall of 2015, Nathaniel Cook, who's right over there, joined the team, and we started designing Capacitor, which is our engine for processing and working with time series data. And I thought, okay, this is a chance for us to come up with a language that's more functional in nature and hopefully will be more powerful for working with this kind of data. And the result of that is TickScript, which is the language the Capacitor uses for working with data. Now, there are a couple of weird things about TickScript. One is that InfluxQL kind of bleeds into it a bit because it has to work with the database to get its data. And the other thing is some of the stuff, like when you look at it, it's pretty foreign. It doesn't look like other things that you've seen before. So ultimately with Capacitor, a lot of times the tick scripts have proven hard to debug because the way Capacitor runs stuff, it runs it in the background, it's not interactive. There's a steep learning curve for the language. For the people who are using Capacitor, they tell us how much they love the power of it, but there's definitely, there's a drop-off in terms of the number of users. And to me, like a steep learning curve for a technology is a massive detractor for it. You want it to be easy. One thing we found was it's not really recomposable. The tick scripts would be, you'd have tons of stuff, and because you couldn't define functions, you couldn't like recompose the bits and pieces to more closely match your problem domain and how you thought about things. And really one of the bad things also is ultimately it's a second language. So now for working with time series data in our platform, you have InfluxQL, which is the SQL-based query language, and you have Capacitor's tick script. And if you're querying interactively, you have to know InfluxQL. And if you're trying to do background processing with Capacitor, you need to know tick script. So learning two languages kind of sucks. And basically over the last year, I thought, okay, we've been at this for a while now. We've seen users how they work with the platform, the questions they have, the problems they're trying to solve. So I thought, you know, if I'm gonna think about the 2.0 version of the product, I want to actually rethink everything. I don't want to just make iterative improvements over what we have, and if I see these rough edges, I want to think about what we can do to fix those things. So part of this rethinking everything is like rethinking what the platform is, what the different pieces are, and what their responsibilities are. Capacitor is really just background processing. It's background processing that happens, and it's either stream or batch. And InfluxDB is the storage as well, but it's also batch interactive processing, right? You throw a query at it, and you expect a result back immediately. So ultimately, I thought, okay, what we should do is we should unify the language so that you have the same language to work with, whether you're working with Influx or whether you're working with Capacitor, and we should unify the API so that all the concepts are the same. The difference is you just specify. Do you want a result back from the query immediately? Or do you want this something to be that gets run on a schedule in the background periodically? Or do you want it something that runs all the time processing your stream of data? So this is like the thinking around the 2.0 API is trying to combine these things so they're less of two separate components and more of a unified platform that you use regardless if you're storing and querying data or processing it in the background and monitoring and alerting on it. So let's talk about the project goals. Obviously, one language to unite the entire platform. We want people to only have to learn one thing and be able to do everything they want to do. We want to increase the feature velocity. There are feature requests that have been open for years, and occasionally somebody will comment on GitHub and ding us and say, what's wrong with you guys? Don't you pay attention to your users? And of course we do. The problem is we haven't been able to get to them. So we want to resolve all of these outstanding query functionality feature requests that have just been sitting around. And one of the other big things is we want to decouple the storage from the compute engine. The compute engine is the query processing engine. Decoupling the storage from the compute engine means essentially Capacitor as a project ends up becoming the query engine, and InfluxDB just becomes the storage tier. And there are some nice properties that you get out of that. One, the query engine can be a bunch of shared nothing stateless systems, which makes it really easy to iterate on those and to deploy them frequently. It makes it easy to scale them independently of your storage tier. So you can put them in a cluster scheduler like Nomad or Kubernetes and just have it scale up based on your query demand. Another nice one is workload isolation. So if you're trying to design a multi-tenant system, you can actually have tenants go into separate query processors, separate containers, and be isolated from each other. So this is very similar to how Amazon's Athena works, which is a SQL query engine based on Presto that's layered on top of S3. It uses S3 as the underlying storage tier, and then you process the data. So the other key goal of the project was we wanted to decouple the language itself from the query engine, right? The language is like a human representation of a query, but that's not what the query engine should use to know what to do to process a query. So what we've done is the query engine is actually, it takes a directed acyclic graph that describes the query, and it can be represented as a JSON blob, which means user interface builders and people working in the web could actually define a query and send it to the query processing engine without actually having to deal with whatever the language it is. And the nice thing is that means we'll be able to support many languages. So we can support InfluxQL is a goal, supporting TickScript, right? We need those two for backwards compatibility so that people can continue to use the stuff they already know if they like it. IFQL, which is where a bulk of the new features are going to be coming in. We also want to support PromQL later this year. We'd love to have, parse PromQL into the DAG and send it to the engine. So the other, this is like a weird thing to call a goal, but in my mind, it's a goal for this project to create what I'm tentatively calling a data language. It's not just a query language. What I want to be able to do is I want to be able to perform analytics tasks within the engine itself. So frequently right now when I'm working with InfluxDB and I have an analytics task, I'll write some code to pull data from the database, and I'll pull a subset based on the query language, right? And then I'll write, once I pull it down locally to my laptop, I'll write a bunch of code to do whatever munging and transformation I want to do on it. To me, that's an anti-pattern. Like, I don't want to do that. That sucks. Like, what I want to do is I want to write one thing that describes exactly what I want to have done, and I want to send it to the platform and have it just do it. So in my mind, the language should enable all sorts of complex analytics workloads inside the platform. If I need to write code in another language to actually do some sort of analytics thing, we're not achieving our goal. So the design philosophy for the language. I list this one first because I think it's really important. Nobody wants to write a query. Like, that's not what you actually want to do. You don't want to, even if it were SQL, you don't want to write SQL. Not unless you, I know, enjoy pain. What you actually want is you want insight from your data. You want to see your data, you want to be able to drill down into it, and you want to be able to do things to it, right? So my theory is, it doesn't matter what the language is, as long as we have a user interface that's built on top of it that makes it really, really easy to access your data in ways that make sense to you. So our goal is to create a user interface that's built around the language that people can use to get started, so they don't even need to learn the language initially. So one of the other key things is readability. Readability over terseness. There are, I'll show you some IFQL queries here in a second, but you can definitely see that there are other ways to represent these queries that would be shorter and require fewer characters. But you read far more code than you write. As any developer who's ever seen a bit of code in a project that they've worked on for a while, and they're like, who the hell wrote this crap? What am I looking at? They do get blame, and they're like, oh, I wrote that. Great. So what we want is we want you to be able to look at the code and understand it. We want to optimize for readability. And really this is, it's big in the Go community, so I give them credit for that. And we want to steal that good idea and use it on our own stuff as well. We want to be flexible. We want to be able to add new functions to the language, right, to address those feature requests. We want to be able to modify the language without breaking previous queries that people had already written. It needs to be testable, both for new functions that we write and for user queries that they create. They need to be able to iterate on those queries and test those individual pieces. We want to make it easy to contribute to. This is inspiration from Telegraph. Telegraph's our data collector. So when we created it, one of the design goals for the actual repo, the way the code was organized, was that we wanted people to be able to create an input plugin without knowing about how the entire project was structured or how the code worked. All they needed to know was a tiny subset of the project, which is this is an input plugin, it looks like this, and they could do that. And that's been very, very successful. We only have one developer that works on Telegraph. It's Daniel right there in the back. But we have over 100, I think it's 139 input plugins. I don't know what the exact count is at this point, most of which have been contributed by the community. As an open source project, Telegraph actually has as much or more velocity in terms of external contribution than InfluxDB does, actually more. So we want to replicate that success, but replicate it for query functionality. And we want to enable code sharing and reuse. The best code is no code at all. If you have to, the less code you have to write to solve your problem, the less likely you're going to introduce a bug, the faster you're going to be able to get to a solution. All that stuff is good. All right, so finally, I'll just go through a couple of examples really quick, and then we'll dig into the elements of the language. So I'll present these without too much explanation. So here, we're just getting the last value for anything written that was tagged with the host tag server0. And the results end up looking kind of like a table where we can see we have a time, field, measurement, host, region, value. And we have, in this case, I have two different measurements that have been written in, usage system and usage user. Here we're getting the last minute of data for a specific measurement on a specific host. And the results look like this. So it's an individual time series where we're getting a minute's worth of data. Here, we're getting the average in 15-minute windows of time for the last hour. And because I said I had 2 fields on this specific host, we're getting 2 separate time series back. So now we can dig into some elements of the language. The first thing to note is that it's functional. This should be expected because I've been talking about how much I love functional stuff for querying time series data. You have built-in functions, which are just there in the language, right? From, filter, and range are examples of built-in functions here. You have anonymous functions. So the filter function takes as an argument an anonymous function that tells it how to filter. And we'll dig into that one in a second. There's this thing, which is the pipe forward operator. It basically says to take the output from the last function and forward it on to the next function in the chain. One decision we made was that we went with named parameters only for function calls. And we did this because we didn't want to do positional arguments. So named parameters have a few advantages over positional arguments that I can see. The first is readability, right? You can look at this and you can see, oh, start is the start time. You don't have to know the function definition to know what the arguments are actually doing and what they're for. The second one is flexibility. If we want to add new arguments to a function, as long as they're optional arguments, we can do that and we won't break people's code that they previously had. Whereas with positional arguments, the second you add new arguments, you're making a breaking change to the API. So a great thing about a functional language is that functions have inputs and outputs, right? And what that means is it makes them really easy to test. You can write a whole suite of unit tests around a function and be sure that it's behaving the way you expect it to build, or to work. And the other thing that I think that you get out of that is it's easier to create a user interface, a builder around the language itself, right? If you look at the way Grafana works, if you look at its user interface for Graphite versus the one for InfluxDB, I think the Graphite one is actually really, really nice. And that's because the Graphite language is functional. You basically select a function, you create the arguments, and you go to the next one and go to the next one. And the other nice thing about that is you can see intermediate results as you build up your query over time, as you chain these functions together. So we'll talk really quick about the inputs and outputs. So the from function actually doesn't get an input. It basically just says what database you're selecting data from. So in theory, the output of the from function would be the entire contents of the database. You then pipe that to the filter function. So it takes that entire contents. And then the filter function has this argument, this anonymous function. This anonymous function actually also has an input, but in this case, the input is a single record, right? And at the bottom, I have an example of a record. It just looks like a flat JSON object, right? Where you can see there's a measurement field, all this other stuff. This right here, that's a tag key that we're matching against. So R is the record. We're matching against the host tag key. Just like in JavaScript, you can access it like this. One of the things we have, because everything now is represented is in the same space as tag keys, we have this idea of system attributes. So those are things that begin with underscore. So, and those can also be accessed like the JavaScript style as well. So measurement and field are present for any InfluxDB data that you have in the system. Later versions, you'll be able to actually write data in without specifying a measurement and a field name, or you can continue using those. The nice thing about this model is that it works both with the way InfluxDB 1.x works, and it works with where things may head in the future. It also works well for how we store Prometheus data inside of InfluxDB. So the other special property is underscore value, which exists for all series. That's the actual value in the time series for a given record. So the filter function output this anonymous function, its output is just a Boolean that describes whether or not the record should be in the set. And you have a bunch of different operators, not equals, regex matches, and some other stuff. You can insert parentheses to create more complex Boolean matching logic, right? Just like you could in like a where clause or like in a search engine or whatever. Here's an example of longhand function definition. So before, we didn't have any sort of wrapper around it. In this case, we're wrapping, where is it? Hold on, there we go. We're wrapping it in curly braces, and if we're doing that, we actually need the explicit return to say to return that. So the output of the filter function is obviously the set of data that has now been filtered down to only the data that matches host is server 0. That gets pipe forwarded over to range, which then further filters the data set down by the last minute of data. And the output for range is the actual final query result.
And it's not the last hour, it's the last minute, right?
In this case, it's the last, oh yeah, that's, comment doesn't match the code. This is why, yeah. So basically, the great thing about this style of the language, I think, is that you have isolation, right? You can think of functions as basically share nothing, side effectless things that receive an input, do some sort of transformation, send an output. Now, even though we see the query like a certain way, it may or may not be executed in that way. So I've seen this question come up with regards to this language, is does the order matter? So here we have a query on the left, a query on the right. In the two, the range and the filter order are switched, right? But if you were to execute these two queries, the results are exactly the same. So if the results are the same, does it matter? Well, here's a new function on the bottom. Is this function the same as the top two? Would you get the same result? And you wouldn't, because we moved max. Instead of max being the last call, it's moved to before the range, and that changes the semantics of the query. Here, it operates on only the last minute worth of data. Here, it operates on data for all time, and then it passes over to the range function. And the truth is, because of that, you're likely to get a max value that's older than a minute old, and then the range function would further filter the set down to the empty set. So the query planner, the IFQL query planner, it will do optimizations while maintaining the query semantics. So order does and doesn't matter. Basically, you should not worry about order generally when it comes to trying to optimize the query, because the planner should do that for you. But you should worry about order if you think about the query semantics. So a bit more on optimization. So the question is, these two queries, would they be the same? Now, if the planner were to take these two queries and execute them exactly as specified, because of the way the database works, the one on the left would actually be more efficient, because it selects a couple of time series first before it actually goes to those time series and filters down the range. But the truth is, the planner will take these two, and the query DAG is different. The query DAG is basically what the user specified as a JSON object. The plan DAG is basically what the planner comes up with as the most efficient way to execute that query. So the plan DAG for these two queries would actually end up being the same. So one side note, though, is that value is a special field, and when you're looking at values, you actually have to look at the time series data. So if you do this on the left, that actually does a full table scan, right? Of the series that match the top three criteria, it will do a full table scan for that value. So putting the range first would actually be much more efficient. Okay, so we have variables and closures in the language. So here we're assigning DB, the myDB measurement to CPU. We have the from clause, the filter, and we can see the anonymous function. And there we're using the measurement variable. So it's creating a closure over the surrounding context. We can also assign functions to variables. So this is basically a user-defined function. So here, let's work through a quick example. So here's a query that we have. Let's see, like, say we had this little bit of boilerplate, and that's occurring like all over the place, and we just wanted to pull that out into a separate function. We could do that like this. So we're just going to call the function select. It's going to take a database name, a measurement name, and a field name. It's going to do a from and do a filter, and then return that. So here's how we call it. We say select, database, measurement, field, and then we can keep doing function chaining on top of that. So we can take the result of select and then further filter it down if we want to, or do a range, or do aggregates, or whatever we want to do. So one thing to note is that if we try call select without the database argument, we'll get an error because it's expecting the database argument. So that leads us to default arguments, another feature of the language. Here, we're saying the default for database should just be MyDB. So that way, we can call it without actually specifying the database, and it'll work. We can also return multiple results to the client. So we can have a whole set of queries that we're going to do and yield all those results. So in this case, we have data, which is just being assigned this window of data, right? This windowed range of data. And then we want to return 3 separate aggregates, the min, the max, and the mean. And we name those results. So basically, in the result format, you'll see, okay, these are the results for the min aggregate. So users can also define functions that are pipe forwardable. So that's this thing right here. So we're saying there's a table argument, which is optional because the equals, and there's the little receives a pipe forward thing. So basically, we can call it. So in this case, we've created a function called mf, which will filter down to a measurement in a field. So in this case, we'll call from, we'll pipe forward that forward to mf, and then we'll pipe that forward to filter and do last. And the nice thing is the query planner will actually execute mf and filter in one go, as opposed to trying to execute one and then execute the other. This is another one of those cases where the plan DAG will look a bit different than what the query DAG looks like. So you can also pass the input as an argument, right? Because the pipe forward that's expecting is an argument by the name of table, so we're just passing it here as an argument. And you can also rewrite the function to pass it as an argument to filter instead. And the truth is, any pipe forward function in the language can specify the table that it takes as an argument. So if we wanted to, we could write a query like this. So the joke that I have with Michael Tessa, who loves Lisp, is that if we made a purely functional language and it actually looked like that, you would end up writing Lisp, which I contend is a very bad idea, because if Paul Graham and Rich Hickey can't make Lisp popular, neither will we. So thankfully, I think the pipe forward operator makes it a bit easier to digest. So the easy to add functions bit. The code in the IFQL repo is organized in a certain way. There's a directory called functions. So every single function that's built into the language has a code file that's ideally named the same thing as the function, and it has a test file. I'm not going to get into how you do all this, but basically, it's 3 screens worth of code. And in those 3 screens, it defines the parser information, the validation, and the execution. Everything you need to know about a function in the language is in that one file. That means anybody who wants to contribute a new function, they don't need to know how the executor works. They don't need to know about the tens of thousands of lines of code that exist elsewhere in the project. They just need to know the interface for defining it and what they want to do, the 2 files. But we also wanted to make it so that people could write code and contribute functions without having to write Go code and recompile the project. So this is an idea that we have that we actually haven't implemented yet. But basically, we want to do imports in namespaces. Right? So here we have a function, a query, and we're calling map. Map is a function that exists, which just iterates over every record in the table that it received. In this case, we're just squaring it, right? We're squaring the value. So what if we wanted to create a shortcut for this? Well, we'll create a function called square. Looks like this. So take a table and send it to map and square it. And we're going to put that into a repo called Pauldix IFQL math, which later we can then import, like you see in Go, and then we can call it. So this is just the namespace qualifier there, IFQL math dot square. So we call that. All right. I have to blaze through the last few things really quickly. So wanted to show some more examples. So this works today, math across measurements. This has been like a 3-year-old feature request, and you can do it now. So we're getting the foo measurement, the bar measurement. We're joining them together. In this case, we're just adding the values. You can add, divide, subtract, multiply. You can put them together so they exist in the same record and give them different names. Having query, another long-standing request. We have 10-minute windows, the mean, and then we're filtering it down to only the values that are greater than 90. Grouping data together, we can get the average utilization by region, right? So we're grouping by region. You can group by multiple keys. Getting metadata. So here, we're doing from, filter, range, and we're calling a function called tag values. Now, tag values actually isn't a function that exists today, but I wanted to show an example of how you get metadata. So this is what the underlying actually raw query would be without the tag values thing. So we group by measurement. We say we want to keep the host value, and then we want to get the distinct values for host. The interesting thing is that it exposes functionality that you actually don't have today as well, which is you can get information about the metadata for any window of time. Right now, our index is basically global for all time. So if you want to see the unique host, that's for all time. In this case, we're seeing what host reported data an hour ago, 2 days ago, or for over an hour period that was 2 days ago. So the tag values function would look like this. And we'll add all sorts of helper functions like this into the language so people don't have to write complex like raw queries. But I think showing this shows the power of being able to define your own functions and basically build the language up around the problem you're trying to solve. Here we're getting the cardinality of it, how many hosts. And you can do that for the measurement names, field names, and all that other stuff. So this is an example of functions that are actually implemented as IFQL, not as Go. And we already have examples of this in the language. Nathaniel did recently the top and bottom functions and like highest average and this kind of stuff. And he actually wrote all of that code in IFQL. So basically, you have this sort limit function, which is able to sort the data. By the way, sort also means you can do all sorts of crazy sorting things that you aren't able to do in the language now. And then the top function uses that. So let's talk really quickly about the project status and timeline. Wrap this thing up. So right now, we're doing a lot of work around the 2.0 version of the API. We want to, as quickly as possible, we want to lock down the request and response format so that library authors and user interface builders can start building around it before everything else is finalized. One of the things I will say about the 2.0 API is that it's going to be available via gRPC or REST, and we're also looking at doing a GraphQL interface to it as well to help, again, help with front-end builders. Another thing that I'm excited about is Apache Arrow. So as I mentioned, I want to be able to do analytics tasks within the processing system itself. But it'd be nice if I could do it in other languages as well. So for those of you that don't know, Apache Arrow, and I'll just read this off the slide really quick, is a cross-language development platform for in-memory data. It specifies a standardized language-independent columnar format for flat and hierarchical data organized for efficient analytic operations on modern hardware, which means it can use things in the CPU to actually make things really, really fast. And it provides libraries, computational libraries, and zero-copy streaming messaging and IPC. So this diagram up here is what you see basically in the big data space. When you're transferring data around, they have all this overhead because you constantly have to marshal and unmarshal data and copy it around and all this other stuff. So the picture on the right is like the dream world that we all want to live in, which is you have one format, and no matter what project you're working in, you can work with that data and work with it really fast without having to copy it around. We're going to be using Arrow as an interchange format internally, but we're also going to enable users to pull that back so they can work with the data in whatever big data library that they like working with. Stuart Carney, one of our developers, started this basically just like 3 weeks ago and did a bunch of stuff around it for basically a native Go implementation of Arrow that takes advantage of a bunch of crazy performance stuff. And it's up on InfluxData/Arrow. The awesome thing that happened last week was Wes McKinney, who is the founder of the Arrow project, noticed it and said, well, Apache Arrow doesn't have an official Go implementation, so he asked if we could add it to it, and we're going to be contributing our code to the Apache Foundation so it could become the official Go implementation of Arrow. So we'll be making an official announcement about that probably in a week or so. So the other thing we want to do is finalize the language. We need to do a bunch of actual work with it ourselves as users, and we want to see feedback from the community to make sure that it has the features that everybody needs, and also that the language makes sense. It's easy to work with. So later this year, we're going to ship IFQL, version of IFQL that works with our enterprise product 1.6. Currently, IFQL works with the open source 1.4 or greater of InfluxDB. We'll have official production level support and working with enterprise later this year. So the other key thing is tomorrow's workshop day. So included with the conference is the workshop day. You just need to tell somebody at registration if you want to come. But the workshop runs in 2 tracks. One track is basically the beginner's track to teach you about the platform. The other track is more advanced stuff. And we'll be running, at the beginning of the day, a workshop on IFQL to get people hands-on with it and also to see what their experience is. And we'll also have a lab to run to see how the language looks to you. So that's all I have. Thank you. Do I have time?
Absolutely.
I have time for questions. Yes.
There's a mic that's coming to facilitate your question.
I hear your comment about Lisp, but functional programming is back on the rise from 50s, and there are plenty of other programming functional languages right now.
Mm-hmm.
Why yet another one?
Oh, why didn't we just use some other language?
Yes, other than probably you don't want to go to JVM route.
Yeah.
And commit to Go, but still there are good languages around.
Well, I mean, so if we're going to make it work in our platform, we would have had to implement whatever that language is in Go. So basically, we would have. Because
you hate JVM?
Yeah, it's not that I hate the JVM. It's that I don't want to deal with transferring the data around and all this other stuff. The goal still is separately, we want a single binary that is able to run the thing in its entirety, and that thing needs to be able to run on all sorts of architectures, including ARM. So basically, we're committed to using Go. So if we say we wanted to do Haskell is the language, okay, so then we have to implement Haskell as a pure Go implementation of it, which is, I'm crazy, but I'm not that crazy.
But you're still implementing some language. Why that language not to look like Haskell or Clojure or whatever?
Aesthetics, I guess. I don't know. There are a million languages for doing things, right? I mean,
Now a million plus one.
yeah, well, exactly. I mean, many people who go through CS, right? If you take PLT, you implement a programming language. So, I guess like the goal is to create something specific to our problem domain. It's not supposed to be generalized to any possible thing you can do. Originally, we started like with it's going to be declarative, which obviously we've branched off from there. So we're not trying to solve any problem you would want to solve in the language. We really want it to be scoped to this. So, yeah.
Thank you.
Would you mind waiting for the mic so everyone can hear? Thank you.
Yeah, just real quick, where was the code? You said if you want to write your own functions, where in the tree can I go find that Go code?
So github.com/influxdata/IFQL is the repo. And then in the repo, just look at the functions. Is it just top level, right? Yeah. Yep, IFQL on GitHub. Yep.
Question on pipe forward functions. Are they optimized? Like if I'm using same pipe forward functions 3 times with different lower pipes?
You mean do we like create new copies of the data every single time?
Yep.
If it's no, yeah, it's optimized.
Okay.
Yeah, like functionally, you can think of it as it's creating a new copy, but that's not actually what happens under the hood.
So I'm glad to see the cross-measurement arithmetic being something that we can now accomplish, because it was one of those things as a kind of a big graphite shop we do a lot of in our analytics. One of the issues we run into with Influx is, or any time series database, is data with very disparate temporal resolution.
Mm-hmm.
And I think one of the things that a time series language could do is offer us some intuitive ways to sort of declare kind of a resolution for the operation or the function. The group does that, but to me, like even just taking it to the level of being a little more intuitive or sort of like namespaced to the function would be, I think, a powerful feature.
Yeah, so you can use tag keys like that today. The 2.0 API will have endpoints to assign metadata to time series, to tag, basically to a filter combination. So you can say anything that matches this filter has this metadata. So some of the metadata could be the sampling rate, all that kind of stuff. I have one more, I guess, and then I'm getting booted off stage.
How would the decoupling of query engine from the data affect the performance? Would some aggregations be done on the database side for the data locality to be more efficient?
Yeah, so the way it's going to work, and this only works right now for the sum and count operations, but the way it will work is intermediate processing will be pushed down to the data tier. So if you're looking at, say, 1 hour windows of time for the last 7 days, and you're looking at, say, the min for that, it would push down the min processing for the 1 hour windows of time, so only the summary ticks get sent back up to the query processor, and the query processor then combines them up. Not everything will be able to be done that way, so we are just trying to make it as efficient as possible to transfer a lot of data quickly. So that's using arrow as the interchange format between the data nodes and the query processors. We're not done with that yet either. At this point, we're not doing, like we have the ideas around what we need to do to optimize performance, but we haven't done any performance optimization yet. We really want to make sure that the language has all the functionality we need and that it makes sense. And then we go about the performance optimization stuff. But some things actually are already faster with IFQL than they are in the old language, just because the way the engine works is, there are a couple of things that are a bit better. All right, that's all the time I have. Thank you, everyone.